Hello, dear students. So today we are going to take introduction to Boolean algebra. Here we'll be focusing on the Boolean algebra laws, Boolean functions, operator, precedence, Boolean algebra function or expression, canonical form, and the simplification of Boolean functions. Okay, so with that outline, so let us move forward. The introduction to this Boolean algebra. Boolean algebra is used to analyze and simplify the digital or logic circuit. It is mainly the purpose of this Boolean algebra. It uses only the binary numbers. Here it is 0 or 1, as you know. It is also called as binary algebra or logical algebra. It is a convenient way and a systematic way of expressing and analyzing the operation of logic circuit. The Boolean algebra was invented by George Boole in 1854. So with this one, okay, here we have a Boolean operations. Okay, so here in the introduction also, the variable used in Boolean algebra can have only two values, binary 1 for high and binary 0 for low. I think you are aware in a switch, if you are clicking on, it means that you switch the lamp. If you click on off, it means 0, you switch off. So complement of a variable is represented by an over bar above of a letter or above of a variable. Thus, complement of a variable b is represented as b bar. Thus, if b is equal to 0, then the b bar is equal to 1. If b is equal to 1, then b bar is equal to 0. Another concept you need to know, OR-ing. You see, you start with a big O. OR-ing of the variables is represented by a plus sign between them. For example, OR-ing of A, B, C is represented as A plus B plus C. Logic ANDing of the two or more variable is represented by writing a dot or multiplication between them, such as A dot B dot C. Sometimes the dot may be omitted in this way, where you can write A, B, C without putting those dots. In your mind, you will know that is the ending of three variables. So here we have the most commonly used Boolean operations, AND, OR, and NOT. All those operations are represented using this truth table. As you know that a truth table will give us the logic of each operation. Here we have AND, we have two variables, A and B. Then at the third column we have A dot B. Here A dot B. So as we have two variables, it means that we should have we should have 2 power 2 possible answers. It means that on A we may have the alternative of values of A, where it may have a 0, 0, 1, 1. In B we have a 0, 1, 0, 1. So making or ending all those two variables, we'll have the answer in this column number 3. 0 dot 0 equal to 0, 0 dot 1 is equal to 0, 1.0 equal to 0, 1.1 is equal to 1. This works like multiplication, as you know. Let us move on. All means we take A plus B. So the input are the same in two variables. Then here we have the answer or the output. This works like addition, but the exception would be to the last one here. 1 plus 1 is equal to 1. As a good student in computer science student, you know that 1 plus 1 normally is equal to 2. We write 1, then you carry 0. This is the one that we are writing here. For not means negation. If you have 0, a bar is equal to 1. If you want 1, the negation is equal to 0. Here we have laws. We have laws in the Boolean algebra. These laws will help us to simplify the given Boolean function. Here we have a commutative law, we have associative law, we have a distributive law and absorption law. We have AND law, OR law, De Morgan's theorem, okay, we'll see it, and inversion law. So with these laws we can prove, we can simplify. For example, let us take this one. A plus AB is equal to A. This is simply that we put A out, then we remain with 1 plus B. 1 plus B, the rule says that is equal to 1. A plus 1 is equal to 1. Okay, with these laws and the theorems, we will be able to simplify any given Boolean expression or function. Okay, so what about operator precedency? The operator precedency for evaluating Boolean expression is the first with high priority is parentheses, the second one is not, the third one is and the last is OR. The operator precedence will help us to evaluate a Boolean expression. Here we have an example using the theorems and the laws of Boolean algebra. Prove the following. You have to make sure that if this side, left side, is equal to the right side by using laws of Boolean algebra and the theorems where necessary. Remember that this bar, it means that is over of 2 in this bracket. In this bracket. Okay, so let's move forward. Boolean algebraic function. A Boolean function can be expressed algebraically with binary variables, the logic operation symbols, parentheses, and equal sign. Means that you have binary variables, means that a variable that can take a value of 1 or 0. The logic operation symbols, either AND or plus and so on, and then you have parentheses and equal sign. For a given combination of values of variables, the Boolean function can be either 1 or 0, as you have explained. Consider, for example, the Boolean function here. We have f1, which is equal to x plus y bar z. The function f1 is equal to 1 if x is 1 or both y bar and z are equal to 1, as we know, and if 1 is equal to 0 or otherwise. The relationship between a function and its binary variables can be represented in a truth table. So we can represent the function or the expression with its binary variables in a truth table. To represent a function in a truth table, we need a list of 2 power n combinations of n binary variables. Here, simply, if we have a binary variable, 3 binary variable, it means that you should have 2 power 3 combinations. A Boolean function can be transformed from algebraic expression into a logic diagram composed of different gates. Through the Boolean function or through the Boolean expression, we may have the algebraic expression into we can transform an algebraic expression into a logic diagram composed with different gates by respecting the logic on the expression. We'll see. Here we have a Boolean algebraic function. Consider the following Boolean function. We have f1 with x bar, y bar, z, plus xy bar, z bar, plus xy bar, z, plus xyz bar, plus xyz. You see that each term, each product here, it is made with 3 variables. So this is what you call canonic form. A canonic form, it is where the function or the Boolean function or Boolean expression is made with all variables. Here we have a truth table to represent this Boolean expression. Here you see that you have variable x, y, and z, and the output. So with these 3 variables means that we have a combination of 2 power n, means 2 power 3, which is equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. And remember that the first one is 0. 0, 1, 2, 3, 4, 5, 6, 7. So we represent it each digit with 3 digits. Okay, good. So here we have our output. Okay, this output is related to these values we have. Okay, so assume this is a random in this column 4. It's a random answer from this. It depends on the logic. So now let us see, after simplification means removing the values or variables that are the same. So we may have this one as a short, as a simplified expression. A Boolean function can be represented in a truth table as we did here, but this simplified is called non-canonical form. Why? Because each term is not made with all variables. You see that here you have only 2 and here you have 1. So with this one simplified, we may get a simplified circuit here made with only 3 gates. If we try to design a circuit from this canonical form, you see we will have many gates. So after simplifying, you see that you have a short where it is made with a simple number of few number of gates. Okay. The purpose of Boolean algebra is to facilitate the analysis and design of a digital circuit. The purpose of Boolean algebra is to facilitate the analysis and the design of digital logic circuit. It provides a convenient tool to express in algebraic form a truth table relation between binary variables, express in algebraic form the input-output relationship of logic diagrams. Also, it finds a simple circuit for the same function. This is the key. A Boolean function specified by truth table can be expressed algebraically in many different ways. Two ways of forming Boolean expression are canonical and non-canonical form, as you have already explained. Canonical should have all variables in each term, but non-canonical form, there is no need of having all variables. Canonical form for Boolean function, we have a SOP, which is a sum of product form. The canonical SOP form for Boolean function of a truth table are obtained by ORing the ended terms, means addition of product terms corresponding to the ones in the output column of the truth table. So we keep focusing on the output of the truth table. Then in the output column, where we have ones, we focus on those terms, and then we make ORing or addition or sum of the ended terms, means a product. The product term, also known as the min terms, are formed by ending the complemented and uncomplemented variables in such a way that the 0 in the truth table is represented by a complement of a variable 1 in the truth table is represented by a variable itself. Let us see in the table. You see here we have x, y, z. Our sum of product is this one. We can represent each term here. You see that here we have x, y, z with its values. Then in a function, we focus where we have x bar, y, z bar. It is x bar here, not y, and z bar, where we have a value of z as z bar. Here 0, 1, 0. So we have here. Then another term, this one, it is x, where we have x is equal to 1, y is equal to 0, z equal to 1. It is in this side. Okay. And then here the next one is 1, 1, 0. 1, 1, 0. It is here. Here we have 1, 1, 1. 1, 1, 1 here. Then we take where we have value 1, 1, 1, 1. So we write this expression and we focus on this main term. Here we have min 2, means you count from the first is 0, 1, 2, 3, 4, 5, 6, 7. So here we have min 2, min 5, min 6, min 7. So simply we can write our function this way. It is f1 or f parenthesis xyz, means it's a function of xyz, represented with this canonical form min 2, min 5, min 6, min 7, means it is the first product or first term, second term, third one, and fourth one in mi 2, mi 5, mi 6, and mi 7, which is written in this way. It's a function, it's a sum of those min 2, 5, 6, 7. These expressions are equal, or this notation. This sum, this operation it is substituted with this one. Simply we can write in this way: summation of 2, 5, 6, 7. Decimal numbers in the above expression indicate subscript of the mini-term notation: 2, 5, 6, 7. Good. This is a canonical form. Let us see the product of sum. The canonical pos. Why canonical? Means containing all variables. Pos for a Boolean function of truth table are obtained by adding the already terms. Means you need to have already terms, means the variables added, then we make a product of them. That is why it is called the product of sum. The product terms, each term is called the max term. The previous one is the mini term. This one is max term. So are formed by ORing the complemented and uncomplemented variable in such a way that the one in the truth table is represented by complement, is the inverse of the previous one of variable 0. In the truth table is represented by variable E itself. Let us see. We have x, y, z. 0, 0, 0 give us 0 in this function. Let us see this function 2. You see that here we have x plus y plus z. Here we have x plus y plus z bar. Where we have 1, we put bar. You see, it is a reverse way of the previous ones. Here we have a 0, 1, 0, give us 1. It means that we have x, y bar, and z. Wherever we have 1 is equal the variable with a bar, with a negation. Wherever you have a 0, it is the variable itself. And we keep focusing where we have 1 in our function. So then we take a product of wherever we have 1s. Means that you have max 2, max 4, max 5, max 7, max 8, which is written in this way. So here the remaining, wherever we have a 0, as you know that is a reverse compared to SOP, wherever we have a 0 is where we take the value to be replaced in a function expression here. So it means that we will have m1, m2, m4, m5, m1, m2, m5 joined with dot, because it is a product of sum. This max term is stand for x, y, z. This m2 is x, y, z bar, and so on. So replacing this dot or multiplication will be replaced by this symbol for a product of m1 and m2, m4 and m5. These are the same notation. Okay, having this one, simply you will get this in a simple way. Having this one also, it is simple, you get this one. Having this one, we'll have a truth table in this way. Okay, this is a truth table. Decimal numbers in the above expression indicate the subscript of the max term notation. Okay, here we have an example. Express the following in SOP form. You see we have a short or a simplified. How to get a sum of product? Simply, you have x plus y bar z. We need to get a way of getting a full canonical form. Here you see that we are missing y and z. Here we are missing x only. So how to get it? You put what you are missing. Remember that sum of product, we need to have a sum of missing variables by taking the correct and the inverter of that variable, y plus y bar. For this one, we'll have x plus x bar. Then we use multiplication, or we make a distributive. Then we'll get finally the last one, which has all variables. You see that finally we'll get it in this form by presenting using this mini term. Finally, the final answer is this one. So we express a given function to the SOP. This can be done by searching or doing the exercise. Here there is an exercise. You can do this, the first one, to make it in a SOP form, and you can express this also in a POS. So you can try it, and then we'll check it for the next class. So later I will see what is a simplification of a Boolean function. Here we will focus on algebraic simplification and came-up simplification. And I hope that you will meet for next class, and then we'll discuss. So let me give you the exercise. Thank you for your kind attention.